We were discussing control unit. As I said, the principal function of the control unit is to regulate data movement within the CPU and between the CPU and the external world. Let us start the discussion, continuing with it from where we left, but first let us make a little bit of recapitulation for the sake of continuity. Let's see, this is the diagram we had on our previous class. We said that if we want to move data between two registers, we'll have to have a data path between two registers. For example, here's a data path between RA and RB, RA and RC. Okay. If it is desired that data from RA should come to RC, okay, then the control gate C2 should be open, control gate C5 should be open, the data should be out from RA and should be into RC. Now, one thing I should emphasize that this data path will be the same width as the width of the register. For example, if the width of the register is of 16 bits, the data path should be 16 bit, and in each line of that data path there will be a gate. Okay, and that is true for all of them. Now you see, if we have to now a set of registers like say 3 here, between any two of which you want to transfer data, then we said there will be naturally 6 lines altogether that will be there. That means we will have to have 2 into NC2 combinations that have to have, which basically NP2 combinations n into n minus 1. Okay. Now, as I said that if the number of registers is too high, say 10, in that case naturally data paths, number of data paths transferred to be too high, and it's a jumble up, and therefore what we do is we go to what we say is the bus structure. Okay, here the different registers put the information of the data into the bus, and the register which wants to take the data takes the information from the bus. For example, if we want to transfer data from PC to memory address register, then the C3 gate should be open and C7 gate should be open, so that PC, the data with PC comes into this internal data bus, and that is now gated into the memory address register. With this picture, let us see that how the different states of the instruction cycle is executed. Okay. Now, let us place two pictures side by side. See the situation. Now, in the case of an instruction fetch, okay, say that we want to have that instruction fetch cycle. Now, if we have to have that instruction fetch cycle, you see that the first thing that one has to do is that content of program counter should come to memory address register, okay, because the program counter is now pointing to the instruction that will be executed next, and that instruction has to be fetched, okay, that instruction has to be read. Okay, here what we have done is that we have used this notation that PC is going to memory address register. That extra bracket that we have used earlier while we were discussing instruction set, we have gotten rid of. It is like the programming language statement, as if, for example, MAR is equal to PC, which means that content of program counter is being set to memory address register, the location memory address register. This will mean that content of program counter will come as the content of memory address register. Okay. Now, with this, you'll see that instruction fetch cycle will consist of that content of program counter comes to memory address register, and this means that the gate C3 and C7 should be open. C3 and C7 should be open, right? Then the content of memory location addressed by the memory address register should come to memory buffer register. Okay, this we have shown it this way, that content of memory location pointed to by MAR, memory address register, will come to MBR, memory buffer register. Now, this needs a memory access, okay, which means that address will be thrown, data will come, and then once the data is ready, then that memory buffer register is, content of memory buffer registers is sent to instruction register. For that, we need that C9 and C1 gate to be open. That means C9 and the gate C1 has to be open. That MBR comes through that internal bus, it comes to the instruction register. Okay. Now, in between, the program counter has to be incremented by 1. I have assumed that each instruction consists of 1 or more words. Every time one word is read, it will consist of 2, 4 or 6 more bytes. Okay, the program counter will be incremented by 1 to come to the next word. Okay, and so to do this incrementation, C0 has to be active so that pass program counter is incremented. Now, this is the steps that have to be followed, okay, if the instruction fetch cycle has to be executed. Okay, this fetch cycle has to be executed. Now, you see that therefore the instruction fetch consists of several sub operations. Okay, we call it micro operations. This is one micro operation, this is another micro operation, this is another micro operations, and this is another micro operation. Now, this operation, as I said, that since it needs memory access, memory read will involve something more, which will come after some time. Okay. Now, let's take another example. Say we want to have a direct addressing. Let us take an example in terms of a concrete instruction. Okay. Let's say I want to move information, so the location data to R3. That is a direct addressing addressing mode, and this is a register addressing mode. Okay, let's assume that these instructions is translated into 2 words. One is that instruction word which contains to move the register R3, and this means that memory direct addressing is involved, and the direct address is kept in the next word. Okay, this is the address for the data. Now, let's see what are the micro steps that is involved here. Now, since this is an instruction fetch has to be done, which means this instruction fetch micro operations will be first executed T1 at time T1, T2, T3. Okay, these I am marking as time instant T1, T2, and T3. Okay, now after that, once the instruction is available at instruction register, okay, that instruction is now instruction register content is decoded, and noting that there is a memory direct address involved, by looking at this M, the central processing unit will go through a cycle which we call the source cycle. Okay, source cycle. Here, the source cycle will consist of once more several micro operations. The micro operations will be that program counter now will be sent to memory address register once more, because when this instruction has been fetched, okay, the program counter is now pointing over to the data address this. Therefore, if I send the program counter content as memory address register content, basically I am memory address registers is pointing to the memory location where the data address is there. Okay. For that gate C3 and C7 has to be open. Okay, you see the C3 and C7 has to be open, and once more a memory access, a memory read is involved, which tells that memory location addressed by memory address register, content of it will come to memory buffer register, and as it comes to the memory buffer register, in the next time the program counter which is pointing to this should increment it by 1, so that it points to the next word. Okay, therefore here program counter is incremented by 1. Okay. Now, and once you have the data here, okay, in the MBR, that MBR will come, content of MBR will be sent to R3, so that this instruction is executed. We can tell that as if it is an execution cycle. Okay. Now mark here one thing, that to execute this instruction, therefore, first that instruction fetch cycle has to be executed, then a source cycle has to be executed, okay, and then that execution cycle has to be completed. Now, since that execution simply consists of transferring the content of memory buffer register to R3 and no memory access is involved, this can be accomplished immediately after that data at MBR is available. Therefore, you see that as such a separate execution cycle is not necessary. These micro instructions can be executed here itself in parallel with as if the program count, when the program counter is incremented by 1. Okay. Therefore, this instruction can be executed in parallel with this instruction, which means C0, C9, C11, these two micro code, so to say, these two micro instructions can be executed simultaneously this way, right? Now, here let's see one thing, that when we say that this is the microcode for the at T1 timing state, okay, let's call this as timing state, at T1 timing state, that C3, C7 should be open, and since there are altogether 12 control points in this simple system, right, we can talk about as if there is a control word which consists of C0 to C12, so many of data bits, or rather control bits, okay, so many of control bits. C3 and C7 are 1 and all the other bits are 0. Okay, that constitute this operation, that C3 is open and C7 open, that is indicated by this control word, all zeros, C7 1, C3 1. So for incrementing the program counter, and so for transferring MBR to IR. Okay, you see C9, C1, C1 is 1, C9 is 0. Now this we call, say this one, this one, this one, we call the control words. Okay, similarly, therefore you see that instruction fetch consists of as if one, then an operation here of the memory access, then the second control word and the third control word. Okay. Similarly, here we have a control word for this operation, program counter going to MAR, then a memory access, then this is another control word and this is a third control word. These two control words can be merged together to frame this, to make this control word, okay, making these two parallel operation. Similarly, you see, as you're saying, when we're making the parallel operation, the incrementation of the program counter can be done anywhere after T4 and before T6. In fact, program counter to program counter incrementation can be done in parallel to this operation also. Okay. Therefore, basically what we wanting to mean that putting a particular micro instruction, okay, we have some, so to say, flexibility, okay, where we can put this particular micro instruction, okay, constrained by that it has to be done after some operation and before some operation. Okay. Another point, let me repeat that when a memory access is not involved, the execution, for execution we need not go for a separate cycle altogether. It can be done within the cycle immediately after the source cycle itself. Okay. Now let us come to some more example, okay, because this is an important issue that we'll have to take care. Say this is another example I have taken, that register indirect addressing. Let us see what is the situation here in the case of a register indirect addressing. We have taken an example, say add bracketed R2, that means indirect register indirect addressing with R2, and the destination is register indirect addressing with R5, that which means the memory location pointed to by R2 should be fetched, okay. Then it should be added with the content of the memory location pointed to by R5, and the result should be contained in R5 as per our convention of these two address instruction that we are having. The instruction word is this, okay, add R5 and R2 in assembly language, okay. Now, once more you see the first thing that for executing of this instruction that has to be done is that instruction fetch, okay. But after the instruction fetch is over, then the source, it enters the source cycle. In the source cycle, say at the T4 time instant or timing state, that R2, content of R2 should go to memory address register. Okay, let us see, the content of R2 should go to the memory address register, which means that gate C10 has to be open and gate C7 has to be open. Now, as I said that we have put only two lines, one from here and another from the bus to the register bank. We say that this is, we have done it because we said that so the register bank is concerned, transferring from any register to any register will be done by means of multiplexer that is within the register bank. Any register content we want, that should be thrown into the data bus C10, and any input to the register bank, okay, will be thrown into the data path C11, okay. I mean data path which is controlled by C11. Now, with this, let us see that R2 goes to MAR, then memory location, content of memory location, which is addressed by memory address register, comes to memory buffer register. A memory access is involved here, and then memory buffer register, content of memory buffer register comes to the temporary register T. Okay, for that we need C9, C4 to be open. C9, C4 to be open. Okay, this is our source cycle, and after the source cycle is over, since once more a memory access is involved, we enter a destination cycle. Okay, in this destination cycle, that content of R5, which is, you see that almost similar to source, this destination cycle while reading, because both are register indirect addressing, only the register changes. Okay, therefore R5 comes to MAR, then C10 and C7, then content of memory location pointed to by memory address register, okay, comes to MBR, right, it's memory access, and once it is MBR, at MBR, MBR's content is sent to, it should not be T, it should be A, okay. Now for that, you see C9 and C5 gate has to be opened. Now once it is done, see, we enter into an execute cycle. We enter into an execute cycle because the result should go to memory location pointed to by R5. Okay. Therefore, one thing is that first thing that it has to do is that it should activate ALU, right? That activation of the ALU will be done here, right? And what ALU will do once more will be decided by the whatever is the opcode in the instruction register that will be channeled into the ALU here, right? Then after ALU operation is over, the output is available. The ALU is sent to memory buffer register. That means C6, C8. The gate should be open. C6, C8. Okay, and then content of R5. Okay, should be once more sent to the memory address register because that contains the address of the destination, and a memory write cycle is initiated where the content of MBR is sent to the memory location pointed to by MAR. That means whose address is at MAR. Therefore, this is the execution cycle that will be followed. Therefore, you see that total number of things, total number of timing states that we have recorded, except of course at memory access, will be instruction fetch T1, T2, T3. I have not counted memory access. Okay. Then T4, so to say T5, T6. Okay. Here it's memory access, right? Therefore, let's see not counting T5. Similarly, T7, T8, T9, we will not count T8. Okay, here T10, T11, T12, T13. Right, we will not counting T13 here because you know this memory accesses will take much more time because a protocol is involved to transfer data between the CPU and the memory. Briefly, we will discuss immediately after this example. Okay. Now that is the total time that is necessary. Now just compare this with the time that I need to say compute add R2. Say time that I need to have add say R2 to with R5. Okay. Here we will naturally go for instruction fetch. Immediately after instruction fetch, you know the content is available at R2 because it is register addressing. The R2 is taken, content of R2 is taken, added with R5, and the result is stored in the R5. Since we don't have to go out beyond the limits of the CPU, that means to the memory, then immediately after fetching the instruction, that instruction cycle, if necessary, can be, so instruction fetch cycle, if necessary, can be a little bit extended so that this addition is done immediately within the CPU and the result is stored in the CPU. The result is stored in the CPU. That saves a good amount of time if the data are available in the register itself. Okay. Now, with this, let us see that what should be the structure of the control unit. Okay. But before that, and what should the input and output of the control unit, how the control unit should function. But before that, let us see that when we are talking about that memory accesses, how exactly the memory accesses are carried out. Okay. I am coming to a diagram that I have shown earlier also, that whenever some data has to be interchanged or exchanged between the CPU and the memory, a protocol is involved. And the protocol involves the address bus, the data bus, and the control bus. Okay. For example, if memory read is involved, then memory address register, we call the address buffer here, that address is here. If you want to read some data, then we say that memory read, this control line should be on to tell the memory that it wants to read the data. On getting this control signal, memory reads the data at the location contained in memory address register, that means contained in the address bus which has been latched into this address buffer here, data is thrown into the data bus, okay, and the signal data ready is sent to the CPU saying that data is ready. Then the CPU can take the data or latch the data into the data buffer, okay. That is a simple protocol that is followed between the CPU and the memory for reading, okay. Similarly for writing, if CPU wants that some information has to be written into the memory, then what it does is that the location where the memory, the data has to be written, that location is put into the memory address register that may come from anywhere depending upon addressing mode, okay. That address bus content is latched by the memory into the address buffer. The data that has to be read, that has to be written into the memory, the CPU will throw that data onto the data bus and will say to the CPU that memory write by this memory write control line, okay, by exciting this memory write control line. On getting that memory write, the memory takes the data from the data buffer, takes address from the address buffer, writes into the memory location which is given in the address buffer, and this line can once more be used to say that the write over, okay, that means data has been successfully written into the memory location. Now naturally, you see, since the protocol is involved between these two, okay, the signal has to be activated properly in time sequences so that this job of transferring data either from CPU to memory or from memory to CPU can be carried out, okay. I'm showing here a simple, I should say that a protocol signals which can be used for this purpose, okay. Here you see that the entire information has been divided, that means entire total total action has been divided into several timing states, okay, T0, T1, T2, these are clock cycles of the machine, right. Now if, for example, memory read is involved, the say on getting that memory read has to be carried out, that address bus is activated, say at the timing state T1. Is going high means as if that address bus has been activated, okay. The address bus has been activated and remains activated, okay. CPU says memory read. Now as the address is thrown, the memory read control line is also activated, right. Memory write control line is deactivated because it's memory read cycle. Now on getting the address, on getting that is memory read, okay, the memory after some time instance, okay, will respond with the data on the data bus. Some time is involved because the memory has to go through the entire process of collecting the data from that address location and then throwing the data into the data bus. That is, for example, after T2, T1 time, we do not exactly know that how many such timing states may be involved. Say after T2 at the tkth timing state, the data has become available. Now as the data has become available, CPU says the data is ready by means of this control signal, okay. Now on getting this control signal, the data ready, the CPU possibly at tk plus 1th time instant, okay, or timing state, the data will be stroked into the data bus, and on that data ready signals will be withdrawn, data bus signal will be withdrawn, okay, all data on the data bus will be withdrawn, memory read signal will be withdrawn, and the address bus signal will be withdrawn, okay. This is the way that entire, I should say, that signals, a possible, I should say that a possible way of sending signals, protocol signals, and the address information and the data information so that data can be read from the memory, okay. Similarly, and we call it the entire thing from here to here a memory read cycle. One important issue that has to be taken into consideration here is that after address is thrown and after the CPU says that memory is ready, depending upon the speed of the memory, the CPU speed is very high. Okay, memory speed is not that high in comparison to the CPU speed. Okay, therefore, after how many timing instance the data will be available is not known. Okay, in the sense that, for example, if I change memory today, this delay from say T1 to Tk, this k may increase or decrease, right? But one important thing is that when the data is available, that memory will tell data ready, and on data ready, the CPU can stroke the data into the data bus. Okay, during that period of time, since the data is immediately necessary, the CPU has to remain idle until or unless we make some other arrangement for it. What arrangement we can make for it, okay, we'll see in our discussion on memory architecture. Now this is our memory read cycle. Let us see similar situation in the case of a memory write cycle. Okay, say in the case of a memory write, CPU wants to write something into the memory whose address is in the memory address register. Okay, now the signals, this address bus, the CPU activates say at the T1 time instant. Memory read is not activated, memory write is activated, okay, and remains activated. And since it is CPU which is writing the data bus is also activated by the CPU. That means data is immediately ready. Now on getting right that memory write signal, CPU starts taking the data, writes in the memory location which is in that which addresses in this address bus and which has been latched into the address latch within the memory, and on completion of the data write, it will say that write done. Okay, say here it says that write done. On getting the write done, the CPU will start withdrawing that memory write signal, the address bus signal, okay, and the memory will withdraw that write done signal. Okay, now here I have shown a time instance at Tk to Tk as if 3 timing states is involved. It may not be 3 timing state, it may be within the same timing state. Okay, but this is actually to give you a picture that how signals are used, okay, to exchange information or exchange, by information I mean data, between the central processing unit and the memory unit. Okay, that exact nature of the signals and the names of the signals, the number of signals may vary, but this is whatever on the overall is a protocol that is maintained. Now here also one should see that between memory write and write done, the total number of timing states that is involved, okay, is quite a good number and is not known as depend upon the speed of the memory unit. Okay, and therefore during this period the CPU has once more to remain idle, okay, until once more we can do something about it, right? Now with this picture kept, okay, let us see what will be the structure of the control unit. This is the control unit. It's a hardwired unit consisting of interconnections of the logic gates and the flip-flops. Now let us see what are the components. The components are, here there is an instruction register, okay. The output of the instruction register comes to a decoder. Let us see what is a decoder, what we mean by decoder. Say we are talking about a 2 to 4 decoder, say, which means it will have say 2 inputs, I0, I1 and there will be 4 outputs, say D0, D1, D2, D3. Depending upon the combination of inputs of I0 and I1, one of these output lines, D0, D1, D2 or D3 will be high. By that say, if we draw the truth table of a decoder, say I0, I1, the 4 possible combinations can be that 0, 0, 0, 1, 1, 0 and 1, 1. The outputs can be D0, so this is D1, D2, D3. For 0, 0 combinations, only this output will be high. For, this is I0, this is I1, okay. For this combination 0, 1, only this will be high. For this combination, D2 will be high, and for this combination, D3 will be high. Therefore, for one combination here, only one line will be high. Okay. Now, such a decoder is necessary here because that instruction that comes has to be decoded before it comes to the control unit to see that which instruction it is. Okay. Now, as I said earlier, that the instruction can be of fixed format, can be of variable format. I mean, instruction opcode can be for fixed length and of variable length. In the case of a variable length, the decoding circuit turns out to be a bit more complicated than the simple circuit that we talked of here. That if there are, say here, k inputs, naturally there will be 2 to the power k outputs. For one combinations of k inputs, there will be one output high out of 2 to the power k possible outputs. Okay. Now, therefore, this is a decoder input that to the control unit, the external signals also are inputs. The external signals may be data ready, write done, interrupt and such signals. The other input signals can be control flags, memory read, memory write. The outputs are C0, C1 to Cm-1. The control points, the gates that are to be opened by these signals. Here there is another input that's come from the clock. Okay, there is a timing generator, the timing sequence generator, the output of which are T0, T1, Tn-1, say n such pulses. How many such pulses will be generated? That also depends upon that what is the state of the machine, and therefore there is an input from the state to this timing generator also. Now, what is the state I am coming to? Before that, let us see that what exactly we mean by the timing generator. Say this is a clock input, pulses, a train of pulses, a sequence of pulses. The T1 is 1 here, otherwise it is 0, so to say. T2 is 1 here, that means a pulse is here, otherwise it is 0 here, and here it is 0, and so on. That means T1, T2, T3, T4, T5, and so on. It comes in consecutive clock periods. Okay. Now let us come to what we mean by the state. Now, as you see that control unit, the signals that will be generated here will depend upon that what the machine state is. That means whether it is in a fetch state, the source state, the destination state, or say indirect state, or it may be in that interrupt state. Okay. Therefore, we keep a unit, small unit here, which represents a state. Okay. Generally, it is realized by means of flip-flops. Now, initially, it is in the fetch state. Okay. The control unit is in a fetch state. The machine instruction is fetched. It comes to the instruction register. The opcode is decoded. Depending upon what opcode it comes, one of the lines, say D0 to DP-1, I mean P such lines may be high. Okay. Now, on this line high, right? And the state, the control, the timing generator generates the timing pulses, and at every timing pulse, C0 to Cm minus 1, that means M control signals are generated out of this control unit. As I said, we assume that this is a hardwired control unit. That means the entire circuit consists of interconnections of gates, logic gates, and the flip-flops. Okay. Now, once the fetch state is over, if say the instruction contains means that a source cycle has to be entered, okay, that means that to get the source address, or the source operand, a memory cycle has to be initiated, and data has to be read from the memory, then it enters the source state. If not, then it enters the destination state. If neither the source nor the destination cycles is needed, by cycle I mean that if neither the source nor the destinations are to be accessed from the memory, then it means that the operands are in the register, and therefore the operation can be immediately done, and the machine goes back to the phase state once more. Okay. Therefore, basically that either it enters the source state or in a destination state or in an execute state, depending upon exactly what is the instruction and what is the addressing mode of the different operands. I am assuming here that it is a source state or destination state. By that is a two address machine. If it's a single address machine, then only one machine state, I mean that memory cycle, it may enter or it may not enter any memory cycle. Okay. This is therefore is the situation or the function of this control unit. Okay. Just to make the point clear, that we say that the CPU enters separate source, destination or execute cycles or execute states if memory access is necessary. Otherwise, it just extends the previous cycle a little bit, and the job can be performed in that cycle there itself. Okay. Now, with this picture, let us try to see one thing, that if the instruction set is simpler and the addressing mode is simpler, then the hardware control circuit will be simpler as well, which means that we can do the decoding faster and execution of an instruction turns out therefore to be faster, which may lead to that execution of the program to be faster. Okay. Therefore, one objective can be, okay, that keep instruction set as well as keep the addressing modes simple. Okay. Another is that, for example, to emphasize this point, let us see that, say, if we have to memory read, that means operand has to be fetched from the memory. In that case, you see that after the address is thrown, okay, in the address bus, right, and it says that memory read is necessary, the memory will, after getting a request for memory read, it may need many timing states. These timing states are the machine timing states, that means the CPU timing states. Okay. And when the data is ready, then the signal comes to the data bus and the memory informs that the data is ready. Therefore, you see that between this and this, there is a good amount of time, say from say T1, where the address has been thrown and memory request has been generated, memory read request has been generated. To get the data, it takes quite a good amount of time. Okay. Therefore, you see the less the memory cycles that is involved, okay, the faster will be in the execution of the operation, right. Now, that is why saying that lesser the number of memory references, faster will be the execution of a program. Okay, which means that if we keep the number of general purpose registers or the data registers high, in that case execution of a program will definitely be faster. Okay, for example, let us see this. Say we have had a register indirect addressing. You see, after the fetch is over, source has to be fetched from the memory. Therefore, here is memory access involved. Destination has to be accessed from memory. Therefore, you see that memory access is involved here also, and execution has to be done, and the data should go back to the memory, and therefore here is also a memory access involved. Therefore, 3 memory accesses immediately makes the total execution of this instruction quite, I should say, time consuming. Now, instead of that, if the instruction of be that add R2 to R5, where only the register addressing has been given. Okay. Now, this means that both the operands are in the register R2 and R5, and therefore immediately after the fetch is over, since no memory accesses are involved in it, the data can be taken from R2, added to R5, okay, and the result can be sent back to R5 with only one timing state, right? And therefore, no such accessing will be necessary, which immediately means the executions of this program will be quite fast. Now, one important thing that I should mention here, that in all these examples, I have assumed that it's a 2-address machine. Matter remains the same if it's a single address machine or it's a 3-address machine. Okay, because in that case, in the single address machine, only either the source or the destination cycles is there, and in the case of a 3-address machines, there may be at most 3 cycles. Okay, operand 1 cycle, operand 2 cycle, and say execution cycle, where after execution of the instruction, the operand may be sent. Okay. Therefore, the overall discussion that we have made remains same, irrespective of whether it's a single address, 2-address, or a 3-address machine. Right. Now, this is what we call that hardware control unit. One important thing that we should mention here, that during this state, that means after, say, I am reading something from the memory, after the memory read is over, since this CPU is cannot do any job before the data comes, right? The CPU has to remain in that wait state. From between this point and this point, the CPU cannot advance. Okay. For that, the CPU has to go to what we call an wait state, which means under situation that when a memory read or a memory write is involved, another state the CPU has to go to, which we call that wait state. In that wait state, everything remains frozen. Say all the control signals remain 0, and it remains in that frozen state until and unless either a data ready or a write done is inputted. Okay. In that case, it comes out of that frozen state, that wait state, and the control signals starts getting generated once more. The timing sequences signals also starts getting generated once more. Another point that we should mention here, that is interrupt. As we have said, that at the end of every instruction cycle, the CPU sees whether there is any interrupt or not. If there is an interrupt, then the machine goes to that interrupt state to handle that interrupt. Okay, and how this machine handles that interrupt, we'll see later on. Therefore, this is in brief the hardware control unit, and that's all that we discussed today. We'll go to another kind of control unit, okay, in our next lecture. Thank you.